Let's get started. We're going to do something a little unusual right now.
But I didn't
Represent me?
yeah, to invite you.
Okay.
After the whole day, and after 4 days, come 2.5 days, 3, at the Dead Sea. And, you know, some people say long love, but love doesn't stop. So, I don't know. I'm very happy and I'm very privileged to have here with us, I think, a very, very special lady, Dévora, which says something on the name as well, from Northwestern. She's responsible on all the relationship, and I think much more, between the Northwestern University and the rest of the world. Is it a good definition?
Yes.
Okay.
I'm in charge of everything, not responsible for anything. So, yes. So we're going to do something a little different. When we were at the Dead Sea Institute on Monday, Sam Stoop, who happens to be my husband, gave a presentation about regenerative medicine, and Leah and Mira asked me to borrow a few slides and just summarize a different approach to regenerative medicine. We heard from Tal Aviv earlier today, tissue engineering. So this is just a different approach to regenerative medicine. It's very short. I'll take a couple of minutes to show you that. At the request of Mira, I'm a political scientist, so you cannot ask me any questions about the presentation. But if you have questions, of course, I can write them down and ask Sam later. No, I'm Grynspan. So, at Northwestern, we also like the idea of interdisciplinary research, and the size of the university is conducive to interdisciplinary research. So Sam has appointments in various departments, and the Simpson Query Institute shows the importance of philanthropy as well. It's a very well-endowed institute. And the institute brings together groups from chemistry, from engineering, and from medicine in one place. So very good work being done there. Tal mentioned a collaboration with John Rogers, who has a Center for Biointegrative Electronics, Biointegrated Electronics. He is in the Simpson Query Institute as well. So there are different centers inside the institute. Okay. There you go. Oh, my goodness. So I will show you Sam Stoop. It's right here in the middle. And this is Mira, the guilty party for everything. Okay. So regenerative medicine, I don't have to tell you why it's important, why we want to contribute to higher quality of life. We're all living longer. We always say 120. So I plan 120 at least. And I keep telling Sam, depending on where it hurts, to hurry up with his research, whether it's cartilage or bone or whatever. So there are many targets of regenerative medicine. Paralysis, of course, and problems typical of the aging population, Parkinson's and stroke dysfunction, diabetes, cartilage and muscle repair, disc regeneration. We all have problems with our backs, kidneys and bones, fractures of all sorts. So everybody's trying to regenerate tissues and to solve these problems in many different ways. So I'm going to describe one platform that is a little different from what Tal talked about earlier. So Sam's platform has to do with self-assembling nanostructures. He designs materials that self-assemble into functional shapes, whether they look like a mushroom or a long fiber or many other shapes. And his approach is not to implant or transplant tissues into the body, but to get our cells to do the work. So how do we trick our body into repairing itself with these nanostructures? So the most important one that he works on tries to mimic, and it's all biomimetic, he tries to mimic the fibers that appear in the external matrix of the cell. So here you have the matrix, a lot of filaments, a lot of things. And what he tries to do is to design these long fibers that resemble the extracellular matrix, but also talk to the cells. And so they're designed to have charges and signals to do different things. And this is the way they look. They're very long, a lot of surface area, very long fibers. And they self-assemble, okay, or not, here. They self-assemble. A purple inside has the programmatic instructions for the self-assembly, and the outside of the filament, of the nanofiber, has signals to talk to the cells. And they're different fibers depending on what you use them for, whether they're for spinal cord, for heart muscle, for cartilage or bone, for Parkinson's, and so on. Okay. Okay. All right. So for those of you who know chemistry, you can read a little bit here, but these are neural stem cells, and the fibers, the nanofibers, recruit these cells, and they generate a lot of new neurons that you can see here in this area. And the important thing about this is that they are not clustered, the new stem cells and the nanofibers, they're separated. And they're motor neurons. These would be the more clustered. You don't want those in the human body. Okay? This is a representation of how it works. You have two ways of signaling. You can bind receptors, or you can bind proteins that then bind to receptors. So this is one representation. This is not real, of course. Sam works with a lot of material scientists and physicists who do the the computer simulations and the models. And then you have this other model in which you have the binding peptides in the surface to bind to the receptors. Okay? All these fibers are designed to disappear in 2-3 weeks in the body after they do their job. Okay? They become gels when you put them in contact with your body fluids. And here you have them in solution. When you inject them into whatever area, whether it's the spine or anywhere else, they gel and they stay in place, whether you use them just as signaling mechanisms or whether you use them to deliver stem cells or growth factors or other. Another example is here. You can see that if you extract some of the liquid and you put it on a puddle here of salt, with a syringe, you can create the nanostructures. It's not a single nanostructure, it's a whole bundle of them. And then you can pick them up and manipulate them. So here is an example for bone regeneration, spinal fusion. There's several models. This is the rabbit in the middle. This is all the blue part is bone. And one of the advantages of this material is that you know that for spinal fusion, they use materials that have a lot of growth factors, that have important, significant side effects. So this material doesn't require that much, 100 times less, which means you can use it not only in the spine for spinal fusion, but maybe in the cervix and other parts of the body that, where you cannot use them now. And the material was developed to be easy to apply by the surgeons at Northwestern. So the idea is to have something that looks like a toothpaste, and it's easy to apply between. To fill in the gap, and then where you put the material, bone will grow, and then the material disappears within 2 or 3 weeks. Right? One of my favorite projects is the one with the spinal cord in Parkinson's. It's a different type of nanofiber, but and it has undergone several transformations. If I can just find this. So for spinal cord injury, this work has been published before. The idea is to create a material that will prevent scarring in the spine, in the spinal cord, and promote the growth of neurons so that they can reconnect. This is very important, and there have been several versions of this material. I'm going to show you this one first. Okay. So this last material just published within the last few months, I think. They discovered that how you design the outside signaling of the material, whether it moves slowly or whether it moves fast, will have an impact on how fast it can bind to receptors and regenerate neurons. So here is some of the spinal cord work. Okay, so this mouse here is paralyzed. This is the control. And when it walks, it cannot move its hind limbs. As you can see, it drags the hind limbs. Okay, that's without any treatment. The original material that the lab has published has a little bit more of mobility. The mouse can drag, but also move a little bit behind it. And this is the material that has the most, or not. Here. And this is the material that I just showed you that has the very rapid movement. Here. Oh, yeah. Here it is. Here. Okay, so this is the latest material, and you can see that the treatment works much better. The mouse can actually bend the hind limbs and walk a little better. So these are just some examples. There is nothing implanted, nothing transplanted. For Parkinson's, it's just an injection, and for this as well, for the spinal cord. And the idea is to get the material to the right spot before it gels somewhere else. Okay, so just a summary of the work, and you can read it in many other places. So, thank you. Yep. All right. So I'm done with that. Now let's start with the presentations for this afternoon. So at Northwestern, we're trying to do something similar. Yeah. There you go. For today's presentations, we're going to have a couple of presentations on the economics of aging. At Northwestern, we're trying to do something similar to what our speaker from Singapore described earlier with the ARISE program. And that is, we have researchers in everything, audiology and speech and regenerative medicine and gerontology, all over the university. The question is, how do we bring them together to create something that has a policy impact? How do we make these people not work together, collaborate? Not everybody can collaborate, across disciplines, but to do a little bit more of that. And the way in which we're doing it is we're going to make it global from the outset. We are partnering with Tel Aviv University and with Singapore and Hong Kong, University of Hong Kong. And the idea is to bring all these people together, not only to collaborate on scientific projects, but also to have an impact on health policy. In the US, of course, in contrast to Israel, for example, we have a lot of people, all elder people who live in institutions. How can we prevent their exploitations, physical abuse, financial exploitation? How can we have better transportation and living arrangements? Urban planning is important. So we're trying to do all of this, but do it in collaboration with our colleagues around the world. And I was very excited to hear about our colleague from the law school here and to hear about designing better products for elderly people. And now we're going to hear about economics, right? How do we allocate resources? How do we adjust to the changing population? And we're not doing that fast enough. And we're going to hear also about research direction in healthy aging in a new economy of people who live much longer. And then we're going to have a panel discussion about how do we do this internationally, how do we collaborate globally. So we first are going to hear from Manuel Trachtenberg. He doesn't have a slide presentation, so we don't have to do anything here in the computer. And Manuel Trachtenberg was just at Northwestern last year sometime, talking about social inequality and in health and economic policy. So today he's going to talk about economic policy and how do we allocate resources to adjust to these new conditions.